In part 2 of the lecture on energy, I will discuss the concept of kinetic energy and conservation of kinetic energy in the context of collisions. Kinetic energy is simply explained as the energy of motion. That means that any object that is in motion possesses kinetic energy. The kinetic energy which we will abbreviate with Ke of a moving object is the product of its mass m and its velocity to the second power. Divided by 2. So the formula for kinetic energy from the definition looks like so. The kinetic energy of an object is the product of its mass m and velocity to the second power divided by 2. What are the units that are used to measure kinetic energy? The units are called joules, and they carry the name of James Joule, who was able to develop the notion about the relationship between work done and change in energy. In terms of basic units, the joule is simply the product of the units for mass and the units for velocity to the second power. So 1 joule is equal to 1 kilogram times meter squared per second squared. Here is the time to state one important fact, and that is that since energy changes from one kind into another, all types of energy will be measured in units of joules. Not only the kinetic energy of a moving object, but also, as later we will see, its potential energy. Heat energy is measured in joules, electrical energy is measured in joules, magnetic energy is measured in joules, and so on and so forth. So all types of energy will be measured in joules. From the breakdown of a joule by base units, it is clear that when you're calculating kinetic energy, the mass of the object must be always converted into kilograms, and the velocity of the object must always be converted into meters per second. One more time, when calculating the kinetic energy of an object, the mass must always be converted into kilograms, and the velocity must always be converted into meters per second. If the units for mass and velocity are not the ones that I just stated, then the calculated kinetic energy will not be in units of joules, and therefore the result of your calculation will be wrong. Let's do 2 examples that illustrate the use of the formula and the definition of kinetic energy. What is the kinetic energy of a car with mass of 1,000 kilograms moving at 36 kilometers per hour? So let's see what we know here. we know the mass of the car, which is 1,000 kilograms, and we know the velocity, which is 36 kilometers per hour. And what we want to find is the kinetic energy of this moving car. From the previous slide, we must remember that the units for mass have to be kilograms, and the units for the velocity must be meters per second. So the units for mass are fine, however, the units for the velocity are not correct. So first, we've got to convert the velocity from kilometers per hour into meters per second. So let's do that conversion. So to convert kilometers per hour to meters per second, we do the following. We multiply 36 kilometers per hour by 1,000 meters per 1 kilometer, and also by 1 hour per 3,600 seconds. So the units of kilometers cancel out, the units of hours cancel out, and then what's left is 36 times 1,000 divided by 3,600. And the units that are left are meters per second. And so when you calculate that, you should get 10 meters per second for the velocity of the car. Now we can calculate the kinetic energy. The kinetic energy is equal to mass times velocity squared divided by 2. This is equal to 1,000 kilograms times 10 meters per second to the second power divided by 2. This is equal to 100,000 divided by 2 kilograms, meters squared, kilograms, meters squared per second squared, which is equal to 5,000 joules or 5 kilojoules. And here I used the fact that 1,000 joules are equal to 1 kilojoule. So that is the kinetic energy of this moving car. A quick correction. 1,000 times 100 is equal to 100,000 divided by 2. That is equal to 50,000, not 5,000. So 50,000 here. And this is not 5 kilojoules, it is equal to 50 kilojoules. Here you go. So that is the kinetic energy of the moving car. Here is a different example that uses the definition of kinetic energy to calculate the speed of motion of a car. What is the speed of a 1,000 kilogram car which moves with kinetic energy of 10,000 joules? So what we know is the mass of the car, and we know the kinetic energy of the car. 1,000 kilograms and 10,000 joules respectively. What we want to find is the speed of the car. So the definition of kinetic energy states that the kinetic energy of this car is equal to the mass of the car times the velocity to the second power divided by 2. So from here, in order to find the speed, I must rearrange the terms and solve for v. So from here we get 2 times the kinetic energy is equal to mv squared. From here we get that 2 times the kinetic energy divided by m is equal to v squared. And now if I take a square root on both sides of this relationship, I will end up with an expression for the speed. So from here, the speed is equal to a square root of 2 times the kinetic energy divided by the mass. Now that I have this relationship here. I can just plug in the numbers for the kinetic energy and the mass and calculate the result. So the speed is equal to square root of 2 times 10,000 joules divided by 1,000 kilograms. This is equal to square root of 20. And now to get the units, remember that 1 joule is equal to 1 kilogram times meter squared per second squared. And then on the bottom we have 1 kilogram. So the units of kilograms will cancel out. And then the square root is going to remove the second power from the units here. And so what we end up with is square root of 20 meters per second, which finally gives us V is equal to 4.5 meters per second. And so this is the speed of the car. Now we are ready to talk about conservation of kinetic energy in terms of collisions. In the previous chapter on momentum, we discussed the 3 types of collisions: elastic, inelastic, and completely inelastic collisions. And I said that, and we also saw that with examples, that the total momentum of a system, or isolated system to be more exact, is always conserved. However, this is not true for the kinetic energy of an isolated system when the collision is inelastic or completely inelastic. However, if the collision is elastic, then the kinetic energy is conserved. So, when a certain collision is happening, if you do not know whether the collision was elastic or inelastic, you can confirm which kind of collision happened by calculating the kinetic energy before and after the collision for the entire system. If the kinetic energy before collision is equal to the kinetic energy after collision, then the collision was elastic. If the kinetic energy before collision is different than the kinetic energy after the collision, then the collision was inelastic. Let's summarize those statements. When elastic collisions are happening, the kinetic energy of a system of object is conserved, which means that it does not change before and after collision. The amount of kinetic energy of the system before collision is equal to the amount of kinetic energy of the system after collision. What is the reason for the conservation of kinetic energy principle to be stated like so for elastic collisions? If you remember, one of the characteristics of elastic collisions was that the colliding objects do not change shape. So if an experiment is conducted of 2 rigid stainless steel spheres colliding with each other in vacuum, where sound cannot be generated, because there is practically no deformation of the material, if the kinetic energy of that system is calculated before and after collision, one would find that the kinetic energy is conserved. This is not the case when we have inelastic collisions, where objects will deform during collision. During inelastic collisions, the kinetic energy of a system of objects is not conserved, which means that the kinetic energy after the collision will be less than the kinetic energy before the collision. So what are the mechanisms of energy loss? There are 3 predominant mechanisms of energy loss during inelastic collisions, and not all of them will necessarily happen during the same collision. It could be a combination of any of the 3, it could be only one of them, it also could be all of them. So we have heat generation because of friction, and this is simple to explain. If you rub your hands, the palms of your hands together, you feel how they warm up. You're generating heat because of friction. The other mechanism is sound generation. So during collision, you will definitely hear sound when the objects collide. Sound is generated by causing the molecules in the air to move, and for that, energy is necessary. So part of the kinetic energy of the colliding objects goes towards sound generation. And finally, some of the kinetic energy of the colliding objects goes towards restoring the shape after collision. As you know, during inelastic collisions, objects change shape. And so, in order to restore shape, some energy must be used. And that energy comes from the kinetic energy of the system before collision. And so, due to those mechanisms of energy loss, after collision, the energy of the system, the kinetic energy of the system, will be less than the kinetic energy before collision. Let's do an example problem that uses conservation of energy to determine whether the collision was elastic or inelastic by comparing the kinetic energies of the system before and after collision. So here is the example. Two model train cars collide. One of the cars is initially at rest. The other is moving at 2 meters per second. After the collision, both cars move together as one. Find the speed of the two-car train after collision. Is the kinetic energy of the system conserved after collision? Assume that the cars have the same mass of 1 kilogram. Since we do not know the speed of the two-car train after collision, first I must find the speed of that two-car train. To do that, I will use the conservation of momentum principle. We are familiar with that principle from the previous lecture, so the calculations will be familiar to you since you've done them already. So here is a sketch of the situation. Before the collision, the first car is moving with velocity v1 2 meters per second to the right, and the second car is stationary with, of course, velocity v2 equal to 0 meters per second. So what is the initial momentum of this system? The initial momentum will be equal to the momentum of the first car plus the momentum of the second car, which is equal to mv1 plus mv2, which is equal to 1 kilogram times 2 meters per second plus 0 kilograms meters per second. So that gives us the initial momentum to be 2 kilograms meters per second. Now let's sketch the picture after collision and let's calculate the final momentum of the system. So after the collision, the two cars are moving together as a two-car train with total mass of 2 kilograms and unknown velocity v. That velocity is what we are looking for right now. So the final momentum of the system Pf is equal to 2 times m times v, which is simply 2 kilograms times v. So the conservation of momentum principle says that the initial momentum of the system and the final momentum of the system must be equal because the momentum is conserved. So if I set the two equal to each other, that gives me that 2 kilograms meters per second are equal to 2 kilograms times v, from where I can calculate the velocity v, and that is equal to 1 meter per second. So now I know all velocities involved in the evolution of the system before and after collision. Now I can calculate the kinetic energy energies before and after collision and compare the two to see if they are the same or if they are different. So here is again the situation or the configuration of the system before collision. We have the first car is moving to the right with velocity 2 meters per second. The second car is stationary. So the initial kinetic energy of the system, Ke initial, will be equal to the kinetic energy of the first car plus the kinetic energy of the second car, which is equal to the mass of the first car times the speed of the first car to the second power divided by 2, plus the mass of the second car times the speed of the second car to the second power divided by 2. And so this becomes 1 kilogram times 2 meters per second squared divided by 2 plus 0, which gives us that the initial kinetic energy is equal to 2 kilograms meters squared per second squared, which is 2 joules. Let's now calculate the final kinetic energy after collision. So after collision, the two cars are stuck together moving as a two-car train with velocity of 1 meter per second, which we found from the previous slide using the conservation of momentum principle. So let's calculate then the final kinetic energy. The final kinetic energy is simply equal to the mass of the train, so 2 times the mass of each car, times v squared divided by 2. That gives us 2 kilograms times 2 meters per second squared divided by 2. Correction, the speed of the train is 1 meter per second squared. 1 meter per second. So the kinetic energy final will be 2 kilograms times 1 meter per second to the second power divided by 2. So this is equal to 1 kilogram meter squared per second squared, or that is equal to 1 joule. So the initial kinetic energy is equal to 2 joules. The final kinetic energy is equal to 1 joule. As you can see, the initial kinetic energy is bigger than the final kinetic energy, which means that there was obviously loss of energy during the collision. And so that means that this collision is inelastic collision. And we know that already by the definition of inelastic collisions in terms of conservation of momentum. In that lecture, I said that when objects collide and get stuck together, that is an example of inelastic collision, and more specifically, completely inelastic collision. And so, in terms of kinetic energy conservation, we know that when the collision is inelastic or completely inelastic, the kinetic energy before and after collision is not conserved. And so we just saw that with this example. Again, the kinetic energy is not conserved, therefore the collision is inelastic.